Imagine a $30,000 GPU rendering, the next great language model. It's processing billions of parameters, doing this incredible work, but is also seconds away from literally melting.
Right, just completely frying itself.
Exactly. And the only thing stopping that silicon from catching fire is this constant invisible stream of chilled liquid.
Mm.
And a software orchestrator watching its temperature millisecond by millisecond. So today, we're looking at the massive shadow infrastructure required just to keep that orchestrator alive.
It's really the ultimate paradox of modern computing, I think. We completely fixate on the AI generating art or solving protein structures, but we sort of ignore the sheer physical violence happening inside the racks to make that possible.
Yeah, violence is a good word for it.
It is. The heat, the power draw, the fluid dynamics. Managing it has really become a computational nightmare in its own right.
Which is exactly why you, listening right now, are here for this deep dive. Today, we are unpacking the SuperCloud Composer architecture, or SCC. We're looking at high availability, the strict sizing guidance required to run it, and really how data center management has been forced to evolve.
Absolutely.
Because we are no longer talking about a single management node pinging a server every 5 minutes. We're talking about a highly distributed, multi-node Kubernetes platform orchestrating the survival of a liquid-cooled AI factory.
And that transition moving from a single server app to a distributed K8s platform, that is exactly where we have to start today. Because if you don't understand that foundational architecture shift, well, the math of how we scale this later just won't make any sense.
Right.
We are fundamentally leaving the era of the monolithic application behind.
So let's dissect that monolithic failure state. Because historically, when you bought data center management software, you just got a giant monolith, right?
Yeah, pretty much a massive black box.
Right, like the UI, the database, the polling engine, the event logger. It was all compiled into one massive code base running on one physical box. And if it struggled to keep up, the solution was just brute force. You just, throw more RAM at it.
Brute force, which inevitably fails at scale. I mean, in a monolith, all those internal components are sharing the exact same memory space. They share the same CPU threads, the same disk I/O.
They're all competing.
Exactly. So consider the failure mechanics here. If your event logger hits a bug and starts leaking memory, it doesn't just crash the logger. It triggers the Linux OM killer, the out-of-memory killer.
Oh, right. The OS just panics.
The OS panics. It sees this giant monolithic process consuming everything, and it terminates the entire application. So suddenly your database goes down, your UI goes dark, and your telemetry just stops dead, all because of a bug in one isolated module.
It's like it's the Swiss Army knife problem.
How do you mean?
Well, if the main hinge snaps on a Swiss Army knife, you can't use the screwdriver or the blade or the corkscrew. You lose the whole tool. But SCC completely abandons that model, right? Because it distributes the workload using Kubernetes.
Yes. SCC containerizes every distinct function. So the telemetry ingester is its own container. The UI renderer is its own container. The database is isolated. Kubernetes essentially acts as the maestro, dynamically scheduling these containers across a cluster of nodes.
Okay, so if we have a memory leak in the UI container today, the blast radius is actually contained.
Completely contained. That specific UI pod hits its memory limit, K8s detects the failure, kills only that pod, and instantly spins up a fresh replica.
Wow.
Meanwhile, the telemetry ingester, which is running in a separate container, maybe even on a completely different physical node, it never drops a single metric.
But, but decoupling everything, don't we create a new vulnerability?
Yeah.
Because if you have hundreds of independent containers floating around, the entire system relies on the K8's orchestrator keeping track of them all.
Yes, it does.
If the orchestrator dies, your isolated containers are suddenly flying blind. I mean, they might still be running, but you can't manage them, scale them, or recover them if a hardware node fails.
Which brings us to the mathematical reality of high availability. Protecting the orchestrator is the single most critical mandate in the SCC architecture. And it dictates that the practical minimum for a Kubernetes control plane is exactly 3 nodes.
3 nodes, not 2. Let's really dig into the mechanics of why, because I think a lot of engineers intuitively assume that adding a second node gives you a backup.
Oh, absolutely.
It's that classic active-passive mentality. But in distributed systems, 2 nodes is actually a trap, right?
It is a massive trap. To understand why it's a trap, you have to understand how Kubernetes maintains its state. The brain of K8s is a distributed key value store called etc. Etc. logs every configuration, every pod state, every scheduled job. For the cluster to function, etc. must maintain absolute consistency across the nodes. It uses a consensus algorithm, which means it requires a quorum, a strict mathematical majority, to commit any changes to the database.
So in a single node cluster, the voting pool is 1, the majority is 1,
Yeah.
it operates fine, but if you lose that node, the system is dead. 0 failure tolerance.
Right. So say you scale to 2 nodes. Your total voting pool is now 2. What is a strict majority of 2?
It's 2. It requires both of them to agree.
Precisely. If node A and node B are running, and somebody unplugs the network cable connecting them, node A can't see node B. Node A thinks, I'm 1 vote out of 2, I don't have quorum.
I see.
And node B thinks the exact same thing. This is a classic split brain scenario. To prevent data corruption, etc., intentionally freezes. It locks down completely. Neither node will accept new data, schedule new pods, or recover failed services.
So even if the hardware on both nodes is functionally perfect, the software intentionally paralyzes itself just because it can't establish a majority vote.
Exactly.
That's wild. Adding that second node doubled your hardware footprint, it doubled your maintenance overhead, but it gave you a failure tolerance of exactly 0.
Which is why the architectural minimum is 3. 3 nodes means a total voting pool of 3. A majority quorum is 2.
Right. Simple math.
Right. So if node C catches fire, nodes A and B still hold a quorum of 2 out of 3. The K8's API server stays up, etc., continues writing state changes, and the cluster survives. You finally achieve a failure tolerance of 1.
Now, here is the nuance in the SCC sizing documentation, though, and I want to make sure you, the listener, catch this, because it is a very specific limitation valid through SCC version 3.11.
Yes, this is crucial.
Those 3 nodes provide high availability for the Kubernetes control plane only. The SCC worker services like the actual containers out there pulling telemetry from the GPUs and the CDUs, they are not currently highly available.
That is a critical distinction. Today, those worker services provide workload isolation and scale, but not HA. If a worker node goes down, the specific ingestion tasks assigned to it are disrupted until that node is restored.
Wait, if the control plane is highly available, but the workers ingesting the life or death temperature metrics aren't yet, isn't that backward?
It seems like it, yeah.
Why protect the management layer first? I mean, if the metrics stop flowing, the GPUs melt anyway.
The prioritization comes down to statefulness versus statelessness and really the hierarchy of disaster recovery. The worker nodes in SCC are essentially stateless executors. They ingest data and pass it along.
Okay.
If a worker node dies, you can just provision a new one. K8 reschedules the containers, and telemetry resumes. The gap is painful, but it's recoverable.
But the control plane is stateful.
Exactly. The control plane holds the etc. database, it holds the encryption keys, the network routes, the entire configuration of what the cluster actually is. If you lose the control plane, you lose the cluster permanently. Yeah. You cannot just spin up a new node. You have to rebuild the entire management environment from scratch. This is why the SCC guidelines insist that if you are running a single node deployment where the control plane and workers are jammed onto one non-HA machine, you must have a rigid backup strategy.
Right, like incremental VM snapshots.
Incremental VM snapshots are mandatory. Without them, one hardware failure is just a catastrophic wipe.
Which gives us the context for SCC 4.0, which is slated for Q1 2027, which will finally bring true HA to those worker services. But until then, we have this hybrid reality. We are defending the brain at all costs.
Yes, exactly.
And we need to talk about why the brain is under so much threat. Like, what is generating so much data that we need a dedicated 3-node distributed system just to watch it?
This is where we hit the telemetry tsunami. The physical reality of the data center has just mutated over the last few years.
Yeah, looking at the baselines of the documentation, it is staggering. A traditional air-cooled environment is almost quaint by comparison now. You're monitoring standard CPU servers, some memory, local disks. You watch the fan speeds, the power supply units, maybe pull the BMCs every few minutes.
Right.
And the cooling is just handled by massive CRS units blowing cold air under a raised floor.
In that traditional model, you might be dealing with racks that pull, 10 to 15 kilowatts of power. The thermal mass is relatively low and air is forgiving. If a CR unit fails, the room heats up slowly over minutes or even hours. You have time to react.
But the modern AI factory operates on entirely different physics. You're packing massive density into a single rack. NVIDIA GPUs, high bandwidth memory stacked directly on the silicon, NV switches orchestrating the traffic, NV-link domains DPUs. You're pulling 100, maybe under 20 kilowatts per rack.
And at 120 kilowatts, air simply cannot absorb and carry away the heat fast enough. The thermal density demands a liquid-cooled chain, which means you are suddenly injecting plumbing directly into the compute chassis.
Let's trace that chain, because this is where the telemetry explosion really happens. It's not just a fan RPM metric anymore. We have cold plates directly bolted onto the GPUs and CPUs.
Yes, and those cold plates have microchannels inside them. Coolant flows through those channels, absorbs the heat, and exits through internal server piping.
Right.
That piping connects to a rack manifold, which is basically a giant vertical pipe distributing fluid to every server in the rack.
And then the manifold connects to the CDU, the coolant distribution unit.
The CDU is the heart of the system. It contains the pumps forcing the secondary fluid through the IT gear and a heat exchanger that transfers that absorbed heat to the primary facility water loop, which eventually goes out to the chillers and cooling towers outside.
And every single step of that liquid chain requires intense observation.
Yeah.
The documentation lists the sensors, and it reads like an industrial chemical plant.
It really does.
You aren't just checking if a server is online. You are measuring leak detection tape woven through the rack. You are monitoring the exact flow rate of the coolant in liters per minute. You're measuring pressure drops across the cold plates, supply and return temperatures to the fraction of a degree, pump vibration, valve actuation states.
Oh, and even water quality sensors to check for particulates or corrosion in the loop.
Unbelievable.
And that level of granularity isn't optional. If a pump in an in-rack CDU fails or a valve sticks, you don't have hours to react like you did with air cooling. The GPU cold plates will hit their thermal maximum in seconds.
Seconds.
Literally seconds. The hardware will emergency throttle and shut down, potentially corrupting massive multi-million-dollar training runs. The telemetry must be real-time and it must be relentless.
To put hard numbers to this, the sizing guidance models a 200-rack AI factory. Let's do the math for the listener on the volume of hardware SCC is trying to interrogate here.
Sure. So for 200 liquid-cooled AI rack, you start with the power delivery. Assuming 2 massive 3-phase PDUs per rack, you have 400 rack PDUs. But you aren't just monitoring the main feed, you are pulling outlet-level metrics to track power usage effectiveness per GPU.
Then the cooling.
Depending on the redundancy, if it's a 1+1 CDU setup per row or rack, you could be looking at 100 to 200 CDUs.
Wow.
And each CDU is a complex mechanical system throwing hundreds of distinct metrics regarding pump speeds, fluid pressures, and heat exchange efficiency.
And then the compute payload itself.
Oh.
At a density of 64 to 72 accelerators per rack, a 200-rack estate houses between 12,800 and 14,400 GPUs.
14,400 GPUs plus the CPUs, the NVLink switches, the InfiniBand fabrics. The philosophical shift here is massive. Historically, facilities managed the water and power, and IT managed the servers.
Right, totally separate teams.
Exactly. They used completely different dashboards. But in an AI factory, those domains are inextricably linked. If the facility water supply temperature rises by even 2 degrees, the CDU efficiency drops, the GPU thermal headroom shrinks, and the job scheduler might need to throttle the workload to prevent a crash.
Everything is connected.
Everything. You have to observe the compute, the network, the power, and the liquid cooling as one singular, interdependent organism.
And that single organism is generating hundreds of thousands of data points every second, which creates an immediate architectural crisis for our SCC deployment. If you have 14,400 GPUs and 200 CDUs bombarding SCC with metrics, those 3 control plane nodes we built earlier are going to choke.
They will absolutely suffocate. And this forces engineers to understand when and how to separate the K8's workloads. The guidance outlines 3 distinct deployment phases based on load.
We briefly touched on the small non-HA deployment, a single node running the control plane and all worker services. Great for a lab, terrible for production. Then we have the small HA setup, 3 combined nodes.
Right. So in a combined setup, you have your etc. quorum spread across 3 physical hosts, giving you K8's HA. But the SCC application services, the telemetry ingestion engines, the database, the UI, are running on those exact same 3 hosts.
The documentation explicitly warns against this combined setup once you hit heavy load. But what is the physical mechanism of failure here? If I have a massive CPU and tons of RAM, why does a combined setup still crash under the weight of AI telemetry?
Because of resource contention, specifically around disk I/O and network queuing. Think about what telemetry ingestion actually is. It is an unending, high-frequency stream of database writes. The worker containers are just furiously trying to write temperature and pressure states to disk.
Right, non-stop writes.
Non-stop. At the exact same time, the Kubernetes control plane, specifically that etc. database, is trying to write its state changes. Etc. requires extremely low latency to maintain that quorum we talked about. If the etc. leader sends a heartbeat to the follower nodes, and the follower nodes can't acknowledge it fast enough because the physical disk controller is paralyzed by a flood of GPU telemetry writes now.
Etc. assumes the node is dead.
Exactly. Even though the hardware is completely fine, the disk I/O is saturated, etc. times out, drops the node from the quorum, and if it happens to multiple nodes, the cluster loses quorum and freezes. The data collectors literally starve the maestro of oxygen.
Which forces the transition to the third deployment type,
Yeah.
medium and large deployments with dedicated workers.
Yes. You deploy your 3 dedicated control plane nodes, and you completely isolate them. You do not let any heavy application workloads run on them whatsoever. Then, you build a separate pool of worker nodes and configure K8s to schedule all the telemetry ingestion and database services onto those workers.
So this isolates the failure domain. The workers can thrash their disks all day long, completely saturating their I/O, and the control plane stays perfectly healthy on its own dedicated hardware.
Exactly.
But as an infrastructure engineer, I need to know when to execute that split. I can't just guess. I'm looking at my dashboard for a combined cluster. What are the specific trigger signals that tell me the system is suffocating?
You have to proactively monitor the monitor. The most critical signal is sustained I/O latency on the storage subsystem. If disk writes consistently spike above single-digit milliseconds, etc., is in danger.
And what about the application layer?
You look for queue growth. SCC receives metrics, queues them in memory, and then processes them into the database. If the ingestion rate exceeds the processing rate, that queue physically backs up. It's like traffic backing up on an on-ramp.
Which eventually leads to delayed ingestion. A temperature metric generated at, say, 12.000.000 p.m. doesn't actually hit the database until 12.01.30 p.m. And in an environment where a GPU can overheat in seconds, a 90-second ingestion delay is functionally useless. You're monitoring the past.
Precisely. You're blind. And the final, most glaring signal is sluggish control plane responsiveness. If you open a terminal and run a basic kubectl command like get pods, and the API server hangs for 5 seconds before responding, your control plane is drowning. You must evacuate the worker services immediately.
Okay, so the red lights are flashing on my dashboard. I have queue growth, my API server is lagging, and I realize I need to build a dedicated worker pool. Now I have to look at the physical blueprint of the data center and decide where this software is actually going to live. This brings us to hardware and storage strategies.
Ah, yes, the great debate. Virtual machines versus bare metal.
The source text is unambiguous here. Virtual machines are the strictly preferred deployment model for SCC environments. Bare metal is relegated to, like, edge cases requiring strict physical isolation. But this feels really counterintuitive to me.
Why is that?
Well, if I have 14,000 liquid-cooled GPUs throwing high-frequency telemetry, why would I introduce the overhead of a hypervisor? Doesn't the hypervisor tax the CPU and memory? Why not give SCC direct, bare metal access to the hardware?
It is a logical question, but it stems from misunderstanding the bottleneck. SCC is not running matrix multiplication. It isn't training the AI.
Right.
It is managing the I/O of telemetry. The minor CPU tax of a modern hypervisor like VMware or KVM is negligible compared to the massive operational agility that virtualization provides.
Operational agility meaning recovery and scaling.
Yes. Think about the hardware lifecycle. If a bare metal SCC worker node starts experiencing memory errors or a failing motherboard, you have to schedule a hard outage. You bring the node down, physically replace the RAM, and boot it back up. Telemetry ingestion drops during that window.
Which we don't want.
Right. With VMs, if the underlying hypervisor host reports a predictive hardware failure, you just migrate the VM to a healthy host. Zero downtime.
And for scaling, if my AI factory expands by 20 racks and my SCC worker is bottlenecking on RAM on bare metal, I'm racking new servers. With a VM, I just shut it down, change the allocation from 64 gigs to 128 gigs, and boot it back up in 2 minutes.
Exactly. The agility to resize, migrate, and snapshot VMs is the only way to sustainably manage a constantly shifting AI environment. However, the guidelines mandate a very strict rule if you use VMs. You must configure VM anti-affinity across 3 separate hypervisor hosts.
Anti-affinity, meaning you program the hypervisor cluster to explicitly forbid these VMs from residing on the same physical hardware.
Right, because hypervisors are designed to optimize resources. If they see 3 control plane VMs with relatively low CPU usage, the hypervisor might dynamically pack all 3 of them onto a single physical host just to save power.
And if that one physical host loses a power supply, apply.
All 3 control plane VMs instantly die. You had software HA, but a single point of physical hardware failure bypassed it completely. Your cluster is destroyed. Anti-affinity rules force the hypervisor to spread the 3 control nodes across 3 distinct physical hosts, ensuring true host-level resilience.
That makes perfect sense. Now let's talk about where the data actually lives, because the storage rules in this documentation are draconian.
As they should be. Storage architecture dictates the survival of the telemetry system.
So the first unbreakable rule, the OS disk. Every single SCC node, whether master or worker, requires a dedicated 512 gigabyte OS disk. And the text emphasizes that this disk must never be shared with telemetry data, persistent application storage, or the internal rook-sev cluster.
Never.
Why such a massive isolated boundary just for the operating system?
It is an isolation mechanism against runaway software. Imagine a scenario where a logging daemon hits a bug and starts generating gigabytes of error logs per second. Or a telemetry queue fails to purge old data. If the OS and the telemetry database share the same physical or virtual disk, the disk just hits 100% capacity.
And when a Linux OS hits 100% disk usage or exhausts its inodes, the kernel panics. The entire node locks up, you can't SSH into it, you can't troubleshoot it.
Exactly. You are locked out of a burning house. By enforcing a hard physical or virtual boundary with a dedicated 512 GB OS disk, you guarantee that even if the telemetry database completely fills its volume, the operating system remains pristine.
Right, so the node stays online.
The node stays online, network connectivity remains, and you can log in to safely clear the backlog.
So if telemetry can't go on the OS disk, where does it go? The guide offers 2 paths, internal rook-sev or external NFS-FS.
Internal rook-sev is essentially hyper-converged storage. The storage software runs as pods inside the SCC Kubernetes cluster, utilizing secondary data disks attached directly to the SCC nodes.
So the SCC worker node is running the database app and also managing the physical storage of that database simultaneously.
Right. It scales linearly. If you need more compute and storage, you add another SCC node. It's great for small to medium deployments because it reduces the dependency on external storage arrays. But the risk is domain coupling. Compute and storage share the exact same failure domain.
Oh, I see.
If a physical node explodes, you lose a worker's CPU capacity A&D, a chunk of your distributed storage replica at the exact same moment.
Which is why large deployments prefer the second option, external NFS or SEF-FS.
Yes. In a massive AI factory, you do not want your management compute tied to your management storage. You separate them entirely. SCC runs on its compute nodes, but all the persistent volumes, the actual databases and metrics, are mounted over the network from a dedicated enterprise-grade storage array sitting somewhere else in the data center.
So if my SCC compute cluster completely melts down, my data is safely resting on a NetApp or a dedicated Ceph cluster. I just pave the compute nodes, reinstall SCC, point them at the external storage, and I'm back in business.
Exactly. The isolation allows the compute to be truly ephemeral.
To give you, the listener, a concrete visual of what this infrastructure demands, let's look at the VM sizing example in the source. Because the phrase management software usually implies something lightweight.
Oh, definitely not in this case.
This is anything but.
The sheer footprint is staggering.
The baseline example for a dedicated cluster specifies 3 master VMs and 3 worker VMs. For each of these 6 machines, the requirement is 24 virtual cores, 64 gigabytes of RAM, the isolated 512 GB OS disk, and up to 2 terabytes of fast telemetry storage for the workers.
Add that up, that is 144 CPU cores, 384 gigabytes of RAM, and potentially 12 terabytes of NVMe tier storage, purely just to run the Observer software.
And you can't run that on a shoestring budget. To support those VMs, the documentation recommends a physical foundation of 3 massive hypervisor hosts. Each physical host needs 128 cores, 768 gigabytes of RAM, and 4 3.8 terabyte NVMe drives.
Which ensures you have the hypervisor headroom to absorb node failures. Remember, if one host dies, the VMs have to migrate and restart on the remaining 2 hosts. They need spare capacity to absorb that load.
Right.
It also provides the runway to deploy additional worker VMs as the AI factory scales.
We are talking about nearly 400 physical cores and over 2 terabytes of RAM. 10 years ago, that was the entire compute cluster for a mid-sized enterprise. Now, it is just the scaffolding watching the actual compute cluster.
It's just the cost of doing business at extreme density.
Which brings us to the ultimate question for the architects listening. How do I know when my design requires that level of extreme scaffolding? Supermicro provides a rigid escalation guide and sizing framework. It dictates when a deployment is standard, and when it requires deep engineering review.
It's a triage system, basically. It filters the standard, predictable deployments from the ones that will break the architecture, if not custom engineered.
Let's look at the baseline sizing limits based on environment type. For a traditional air-cooled environment standard CPU servers, no liquid plumbing up to 75 racks, the baseline is simple. 3 combined control plane and worker nodes.
Right, because the telemetry volume is low enough that resource contention on the disk I/O isn't a critical threat yet.
But if that same traditional environment scales from 76 to 100 racks,
You start with the 3 combined nodes, but a product management review, a PM review, is triggered. The engineers must validate if the specific polling frequency demands separating the workers.
now compare that to an AI environment, whether air-cooled or liquid-cooled. Even below 75 racks, the baseline immediately abandons the combined setup.
Yes, for any AI environment up to 75 racks, the starting point is 3 dedicated control plane nodes, PLUS, at least 3 separate workers, and a PM review is recommended immediately.
Because even 10 racks of liquid-cooled AI generate more critical telemetry than 75 racks of standard web servers.
Exactly. The data velocity is exponential.
If that AI system scales from 76 to 100 racks, the 3 dedicated CPs and 3 workers are mandatory, and the PM review becomes strictly required, and for any complex estate over 100 racks.
There are no standard baselines. It is declared a custom design. It requires a mandatory granular engineering assessment of every single telemetry point to build a custom worker pool.
The documentation actually quantifies this difference in telemetry weight by looking at rack types. It categorizes standard compute racks versus AI, LLM, and HPC racks like the NVIDIA B200s or GB300 PowerShells.
This is where we see the physical limits of a single worker node.
So for a standard traditional rack, the sizing guide states that a single SCC worker node can handle the telemetry of roughly 30 racks. And a standard multi-node cluster maxes out around 165 racks before you need extreme customization. But for Type 1 or Type 4 AI racks, the dense, liquid-cooled NVIDIA setups,
A single worker node can only handle 20 racks.
a 33% reduction in capacity per node, and the absolute maximum cluster limit drops from 165 racks down to just 110 racks.
That gap, dropping from 30 racks down to 20, is the mathematical representation of the liquid cooling telemetry penalty. Tracking coolant flow, manifold pressure, and individual GPU cold plate temperatures consumes a massive amount of processing overhead.
To navigate these thresholds, the guide outlines a 4-step validation process for field application engineers. Step 1 is defining the inputs.
This is an exhaustive audit. You don't just count the servers, you document the polling frequency. Are you pulling metrics via IPMI every minute or streaming redfish telemetry every 5 seconds? You evaluate data retention. How long does this data need to live in the database before it's purged?
Right. Then step 2 is measuring the baseline. You deploy a test footprint and capture the actual CPU, memory, and disk latency in the real environment. Step 3 is setting the worker thresholds.
Based on the baseline, you define the exact queue length or I/O latency metric that will trigger an automatic alert, signaling the customer that they need to deploy a new worker node to relieve the pressure.
And step 4 is publishing the escalation rule. It gives the sales and deployment teams a hard line. If a customer asks for a liquid-cooled AI cluster over 100 racks, do not quote a standard SCC license. Route it directly to product management for a custom architectural build.
Because a failure to properly scale the management infrastructure at that level isn't just an IT headache. It is millions of dollars of hardware put at direct thermal risk.
Which perfectly sets up the final deep leads example provided in the source material. This is an architecture built for an extreme edge case in SCC version 3.11, monitoring a 512-drawer liquid-cooled B200 setup.
This is where standard software configurations completely disintegrate.
The physical architecture they landed on was 1 master node and 4 dedicated worker nodes. But what fascinated me was the deep database tuning required. They didn't just deploy a standard Postgres container. They had to alter the fundamental memory and connection management of the database just to survive the influx of data.
Let's dissect those tuning parameters because they illustrate the physics of the bottleneck perfectly.
First, they had to increase the Postgres max connections to 750. In a standard database, 750 concurrent connections is massive. Why is this necessary?
Think about the 512 drawers of B200s. Every drawer contains multiple GPUs, network switches, and localized liquid cooling sensors. Every single one of those endpoints has a microservice or a telemetry agent trying to write its status to the database simultaneously. If your connection pool is too small, say, the default of 100, those agents have to wait in line.
And while they wait in line, the metrics queue in RAM.
Right. And in a thermal runaway scenario, a metric waiting in RAM for a database connection is useless. By pushing max connections to 750, the database allows hundreds of agents to write their telemetry at the exact same millisecond, eliminating the queue.
But every open connection consumes RAM, which explains the next tweak. They modified the work mem to 4 mil and pushed shared buffers to 128 MB.
The shared buffers parameter is critical here. It determines how much dedicated memory Postgres uses to cache data blocks before relying on the OS cache. In a high-frequency telemetry environment, you are constantly querying the most recent data, checking if the temperature 5 seconds ago is higher than the temperature 10 seconds ago.
You need that data in RAM. If the database has to do a physical disk read to fetch a metric from 10 seconds ago, the latency spikes.
Exactly. By heavily tuning the shared buffers and the GRUZ-based group size, which they increased from a default of 20 up to 60, they are optimizing the database to hold the hottest, most critical indexing data in memory, preventing physical disk bottlenecks during massive telemetry spikes.
They even had to tune the Kubernetes layer itself, pushing the kubelet max pods limit on the nodes all the way to 21010 just to handle the sheer number of isolated containers required to run the ingestion services. We are effectively re-engineering the memory allocation of a massive database just to watch another massive computer do its job.
It is a high-frequency trading environment, but instead of trading stocks, the database is trading thermal metrics. The database isn't holding customer records, it is holding the vital signs of the AI.
It's incredible. So let's synthesize the journey we've taken today. We started by exploring the death of the monolithic application. We saw how Kubernetes isolates failures by distributing workloads across containers, turning a fragile Swiss Army knife into a resilient modular workshop.
We dissected the uncompromising math of quorum, understanding why a 2-node cluster is a split brain trap, and why 3 nodes are the absolute baseline for protecting the orchestrator's state.
We traced the telemetry tsunami, comparing the quiet, air-cooled data centers of the past to the intensely violent, liquid-cooled AI factories of today, where thousands of GPUs, CDUs, and manifolds require millisecond observation just to survive.
We examined the trigger signals of a suffocating control plane I/O latency and queue growth, and the strict engineering rules for separating worker nodes onto their own infrastructure to preserve the cluster.
We tackled the necessity of virtual machine agility, the absolute mandate of a dedicated 512 gigabyte OS disk boundary, and the massive 400-core physical footprint required just to run the management layer.
And finally, we saw how extreme scale demands deep software manipulation, tuning Postgres connection pools and shared buffers to process thermal metrics at the speed of thought.
It completely reframes how we look at infrastructure. So the next time you, the listener, see a press release about a new gigawatt AI data center promising to train models with 100,000 liquid-cooled GPUs, look past the shiny numbers. Think about the shadow infrastructure. Think about the unseen SCC control planes, the isolated storage arrays, and the frantically tuned databases churning in the background. Because without that shadow infrastructure watching every drop of coolant, the entire billion-dollar facility melts down in seconds.
It is the ultimate unsung hero of the AI revolution, but it does leave us with a fascinating and somewhat unnerving architectural trajectory.
How so?
Think about the curve we just traced. A decade ago, management software was an afterthought running on a spare server. Today, as AI clusters hit 100,000 GPUs, the infrastructure required just to monitor the system is approaching the size and complexity of a traditional enterprise data center. The observer is growing just as fast as the observed.
The observer effect in IT.
Exactly. The act of measuring the data center now requires a data center of its own. It begs a serious question about the limits of human-engineered software. As these liquid-cooled environments become so unthinkably vast, and the telemetry velocity exceeds the capacity of tuned databases, at what point does the shadow infrastructure become so complex that we have to ask the AI to monitor itself?
Handing the keys of the life support system to the intelligence running inside it. That is a wild, complex thought to leave on. Thank you for joining us on this deep dive into the massive, unseen machinery of AI infrastructure. Keep looking for the shadow systems behind the magic, and we'll see you next time.